Based on the Lorentz force, now we will talk about the torque acting on a current loop, which is within the electric field. So as you can see here, so we have the magnetic bar. Maybe here we have a large north pole, and this is a large south pole. So it is similar to the parallel plate capacitor. Then it will generate a uniform B field between these two poles. So it means we have the magnetic field here pointing to the right side, from the north pole to the south pole, and as much as this is large enough, then we will assume the B field would be uniform between these two magnetic poles. And okay, so this is the setting for the magnetic field, and then we can see another structure. So we can see this one. So it's similar to the barbecue. So this axis can be rotated. So here we have a loop, and then let me see, the current can going clockwise in this figure. So counterclockwise, going counterclockwise in this figure. So in this case, there will be forces acting on this loop. So as you can see, for this wire, the current is going roughly from top to bottom this way. So you can imagine L also point to this direction for the left wire, and the magnetic field pointing to the right side. So you can use the right hand rule to determine that L cross B should be pointing upward, which means the FB for this segment should also be pointing upward, like this. And for the right hand side, this wire, we have the current going this way. So in this case, L point to this side, and then B point to the right side. So you can also use the right hand rule to determine that F should be pointing downward. F should be pointing downward like this. So in this case, actually this loop can't really move. It can only be rotate with respect to this axis. So in this case, this side going up, this side going down. So it will rotate clockwise. So it will rotate us. It will rotate like this. It will rotate like this. And of course, this is actually a torque because it tries to make this loop rotating. So as you can see on the left hand side, we have the cross section. Don't know how to draw. Maybe I can imagine it will be roughly like this. So we try to cut it vertically, and then we will have this figure. So as you can see here, this is one side of the loop, and then here we have the current. So for this one, it should be going out, and for this side, it is going into the page. So L cross B pointing upward because the B field pointing to the right side. So this L pointing to yourself, So L cross B pointing upward, and for this one, L pointing is going into the page, So L cross B pointing to this side. So we have F1 and F3 in the cross section. And this one is the normal vector. Is the normal vector, which is perpendicular to the loop. Perpendicular to the loop. So now we assume this length is B. This length is B. And yeah, so the angle between the normal vector and the magnetic field is theta. Is theta. So now the torque can be derived as this one, NIAB sine theta. So here, N is the number of turn. N is the number of turn in the coil. So which means that it is not necessary to be one turn. It can be something like something like this, and then going the other way. So then it can have many turns. So the number of turns here is capital N. So be careful. In this or the next chapter, we may see some capital N and small n. They specify different variables. Usually N is specified in the number of turns, and small n specify their like number of turns per unit length, something like this. So it's like the turns density. But yeah, but more precisely is like the number of turns per unit length. But here, capital N, it only means the number of turns in the coil. So it's somehow like related to the number of turns. And A is the area. A is the area, which means this area, the area of this rectangle. The area of this rectangle is A. And then I is of course the current, and B is the magnetic field, field magnitude. And theta is the angle between the B field and the normal vector. Well, we did not actually derive it here. But actually you can imagine that, so F is so you can imagine this is the F. F1 is somehow like I L cross B. So it is somehow like ILB. And yeah, when we consider the torque, we need to consider this distance. So it is like this distance is b over 2 times sine theta, because this one is theta, so this one is also theta. So this one is like this one over b over 2 is sine theta. So b over 2 times sine theta is this length. So when we consider the torque, it should be not Fi, should be F1 there. And actually we also have a F3 in this direction. So both forces contribute to the clockwise rotation. So as long as this, we will have F1 times b over 2 sine theta plus F3 times B over 2 sine theta. And actually F1 and F3 should be the same. So F1 and F3 should be the same. So we will have IL small b times big B and then sine theta. Because F1 and F2 are actually the same. ILB. So we have IL capital B and then we have B over 2. So when 1/2 add together, it becomes 1B and then sine theta. So actually L times B is nothing but the area. So it is IAB sine theta. But for this case, it's only for one turn. If we have n turn, then we multiply it by capital N. So it turns out the torque will be like this. So it is actually like a motor. So for a motor, we will have the magnetic field, and then we drive some current into it, and it will keep rotating, So any questions? Okay. So here we'll define another variable called the magnetic dipole moment. So previously we already learned the electric dipole moment. For the electric dipole moment, which is small p, which is let me see, Q times D. So that is the magnetic dipole moment. So now we have the magnetic dipole moment, which is denoted as mu. Mu is the magnetic dipole moment. So now if we want to simplify the torque, previously we have the torque like this, NIAB sine theta. Now we can use mu to gather some of the terms. So actually, for the magnitude of mu, it will be NIA. So if this one is mu, NIA is mu, then it becomes mu b sine theta. So you can imagine mu has the direction as the normal vector, and then so we have mu cross b, which will be mu b sine theta, because the theta is the angle between the normal vector and the magnetic field. So it will be actually torque equals to the mu cross b. So similarly, the potential energy will be minus mu dot b. So we will use these two equations to determine the torque and also the potential energy. The potential energy stored in the magnetic dipole moment. And of course, as long as the mu is a vector, so now it is like maybe I just erase this parts. So for a magnetic dipole moment, it's usually like as long as we have a loop and then we have a current. Or maybe we have n loop. Then the area the area of this loop is A, then mu equals NIA, and the direction will be like this way. This is the direction of the mu, which should be defined by determined by right-hand rule. So you can use your finger follow the direction of the loop, and then the direction of your thumb will be the direction of the torque, the dipole moment, the magnetic dipole moment. So you simply use right-hand rule to define the direction. You use your forefinger to follow this direction of the loop, and then your thumb will point to the direction of mu. So in this case, you can simply try this one. So this one is the current is going clockwise. So that if you use your finger to follow the direction, then your thumb will point to the bottom. And then for this one, if you use a forefinger to follow it going counterclockwise, then your thumb will point to the top. So this is the way to determine the direction of the magnetic dipole moment. And likewise to before, then actually WA equals delta U. So if you need to change the potential energy, then there some work need to be done. Okay, so now we have a sample problem 20. So here so a circular coil with 250 turns, an area A of this one, and a current of 100 μA. The coil is at rest in a uniform magnetic field of magnitude B, with its magnetic dipole moment initially aligned with B. In the figure, what is the direction of the current in the coil? The direction of the current. So actually, the direction of the current will be somehow like mu pointing to the right side. Actually, I do not draw too much turn, because if I draw too much, then it will be just a mess. So I just draw one turn, and actually the direction should be like this. You can simply apply a right-hand rule to determine the direction of the current. Any questions? No questions. So for part B, how much work would the torque applied by an external agent have to do on the coil to rotate it 90 degrees from the initial orientation, so that mu is perpendicular to B and the coil is again at rest? So now we have WA equals U 90 degree minus U 0 degree. So for the U, which will be minus mu dot B, So it will be minus mu, which will be mu b cosine 90 degree, because when it rotates to 90 degree, it is somehow like the B field point to the right side, and then the mu point to the left side. So this theta is 90 degree. So we have mu dot B, which will be actually minus mu dot B, which will be minus mu B cosine 90 degree, and then minus mu B cosine 0 degree. So you know cosine 90 degree is 0. So this is 0. So, and then this is 1. So we turn out have mu B, which is NIAB. So in this case, N is 250, and then I is 100 mu. So 100 times 10 to minus 6, and then times A is this one, 2.52 times 10 to the minus 4th power, and then times B is 0.85. So it will be 5.36 mu joule. Any questions?